In this program, we will explain how rockets and space shuttles work. Then we will tell you about some of the scientific experiments that have been carried out in orbital laboratories. What is a rocket? Today, the term designates any projectile or craft that is not propelled by air, oxygen, combustion. It was in Massachusetts, USA, on March 16, 1926, that the American physicist Robert Goddard pioneered the first liquid fuel rocket. It reached an altitude of 12 meters and landed 56 meters away. The principle of rocket propulsion is simple. When you pump water through a hose, you can feel the force of the water pushing the hose in the opposite direction. Well, the same principle applies to rockets. Of course, it's a little more complicated than that. The third law of movement, formulated by Isaac Newton over 300 years ago, explains how rockets function. According to Newton's law, any action will generate a reaction of equal force in the opposite direction. What propels rockets is the high-speed ejection of gases under great pressure. The gases are produced when fuel is burnt in the combustion chamber of an engine. To burn any substance, whether wood, gas, or paper, oxygen must be present. Because there is no oxygen in space, the rocket must carry its own oxygen supply for the combustion of its fuel. The substance that provides the oxygen is called the oxidant. The substance that burns and produces the ejection gases is the fuel. Oxidants and fuels are propellants, that is, elements which in the absence of oxygen in the ambient air have a combustive chemical reaction. Rocket engine propellants can be solid or liquid. Among liquid propellants, the most powerful combination is the one based on liquid oxygen as an oxidant and liquid hydrogen as fuel. Rockets that use liquid propellants are very flexible. The thrust of their engines can be controlled simply by adjusting the flow of propellants to the combustion chamber. Thus, the engine can be slowed down, stopped, reactivated. However, because the hydrogen and oxygen fuel tanks must be maintained at temperatures of from 170 to 125 degrees below Celsius, liquid propellant rockets can only be fueled just prior to liftoff. Conversely, rockets using solid propellants can be neither slowed down nor stopped. Oxidant and fuel are combined in the form of a compact block. The block is poured into the body of the rocket, which then becomes its own combustion chamber. Once fired, there is no way to control the combustion. It will burn until the solid block is completely spent. Solid propellants do, however, have the advantage of being able to be stored in the rocket a long time before liftoff. Ballistic missiles, which have to be ready at all times and at a moment's notice, use solid propellants for that reason. Whether fueled by solid or liquid propellants, a rocket moves by ejecting from the rear its propellants converted into gas. The rocket's total mass thus decreases, enabling it to pick up speed as the thrust remains steady. As they empty, the propellant fuel tanks become useless dead weights. If they are jettisoned, the rocket speed will be increased. This is the principle that underlies the development of the multi-stage rocket. Each stage is equipped with its own engines and propellants. The stages separate one by one as their propellant supply runs out. Every time a stage separates and the engines of the stage above go into action, the rocket gains speed because the total load is less. Some rockets have as many as 4 stages, but the 2 or 3 stage ones are the most commonly used. Finally, when all the stages have been cast off, only the main one reaches destination. It could be a satellite, the nuclear head of a ballistic missile, a spacecraft, or a space probe. A rocket's trajectory can be broken down into two phases, the propulsion phase and the ballistic phase. The propulsion phase begins at liftoff. It is the phase during which the engines of the various stages are operating. It is a guided phase during which the rocket is given the desired speed and direction. It lasts less than 10 minutes. Then the ballistic phase takes over. The engines of the final stage of the rocket no longer provide any thrust at all. The rocket proceeds solely on its course through space. The device follows a ballistic trajectory, that is, subjected only to the gravitational pull of the Earth. For missiles, the last stage sets its nuclear charges on a precise course. The nuclear heads will go downward to Earth according to a ballistic course and land precisely on target. It's also during the ballistic phase that a satellite is put into orbit. For the next generation of rockets, scientists plan on using nuclear engines. This futuristic approach will develop thrust by expelling ions instead of gaseous combustion products. Rockets like these could be 10 times more powerful than the rockets of today. Thanks to nuclear energy, trips to Mars or other faraway planets may be possible sooner than we think. But nowadays, we rely mostly on space shuttles for space development. The Americans built the first shuttles, but the Russians are making progress on their own. U.S. space shuttles are capable of launching 30-ton masses into orbit. But the major advantage of the space shuttle is that it can be reused up to 100 times. A space shuttle is a craft that can lift off like a rocket, go into orbit around the Earth to perform specific tasks, and then return to Earth where it touches down on a runway like a glider. The first space shuttles were built by the Americans. Since 1981, space shuttles have made close to 30 flights. When poised for launch, space shuttles straddle an immense cylindrical fuel tank. The tank holds over 700 tons of liquid propellant, hydrogen and oxygen, which fuels the shuttle's three main engines. On either side of the main fuel tank are two auxiliary propellers called booster rockets. These booster rockets provide the main thrust for liftoff. The shuttle first lifts off very slowly, wrapped in a white plume. The cloud of smoke is created by the vaporization of huge quantities of water flooding onto the launch pad when the engines go into action. Some 300,000 liters of water per minute douse the pad. All this water protects the shuttle from the shock wave generated by the firing of the engines. Almost immediately after liftoff, the shuttle turns onto its back. It does this to aim toward Earth the various instruments used to analyze different aspects of our globe. Only 2 minutes after liftoff, the craft reaches an altitude of 45 kilometers. It is at this point that the now spent booster rockets separate from the main fuel tank. They fall back into the sea, with 3 parachutes slowing down their descent. They will be reused for a future mission. The shuttle then prepares to leave the Earth's atmosphere and penetrate space. About 7 minutes after liftoff, the 3 main engines are cut off. The fuel tank's propellant supply is spent. The fuel tank is then jettisoned, falling back to Earth and disintegrating as it enters the atmosphere. The shuttle then enters into its ballistic phase, when it is no longer propelled by an engine. It simply continues along its trajectory, subject only to the Earth's pull. When it attains the right altitude, small rocket engines located at the rear provide an extra little boost for a few seconds. This enables the shuttle to gain the velocity required for its entry into orbit. A mere 8 minutes has passed since it left Earth. The force of attraction of the Earth, which pulls the shuttle toward it, is then equal to the centrifugal force that tries to wrest the shuttle away from the Earth's gravitational pull. The astronauts are then in a state of weightlessness. Deprived of gravity, they avoid making abrupt movements that might throw them off balance or project them against the walls or into their fellow crew members. A shuttle can accommodate 7 to 20 cosmonauts for an average period of 1 week. The cabin the astronauts live in, located at the front of the shuttle, is divided into 2 levels. The living space amounts to 70 square meters. The upper level is the pilot station, which holds 4 people. The lower level is the living area. Behind the astronaut's cockpit is the hold. The hold will carry a 30-ton payload, enough for 1 or more satellites that are to be put into orbit. It is also used to repair a damaged satellite or transport it back to Earth. When the shuttle is about to leave orbit to return to Earth, its orbital engines first slow it down. Because it no longer has sufficient speed, the shuttle unhooks from its orbit and falls towards Earth. On re-entry into the atmosphere, the aerodynamic braking system raises the temperatures on the shuttle's exterior walls to some 1,500 degrees Celsius. At one point, the intense heat of re-entry creates an orange-colored plasma around the shuttle, a kind of 4th state of matter, which cuts off radio communications. An insulated armor of 34,000 tiles protects the shuttle from the intense heat. The tiles covering the craft's nose and leading edges of its wings are made of carbon fiber, capable of withstanding temperatures of 1,500 degrees Celsius. During the braked descent on its belly, the shuttle soon reaches the lower and denser layers of the atmosphere. A belly flap is then activated. Instead of braking, the shuttle then dives toward Earth, descending in glider-like fashion. Its speed is then sufficiently reduced for radio communications to be re-established. The shuttle makes a few S-turns to reduce speed even more. It touches down on the runway at a speed of 350 kilometers an hour. Mission accomplished. In a short while, it will be ready to make another trip. A shuttle takes about 1 hour to return to Earth. In most cases, the astronauts have been aboard for several days. While everything is planned to make their stay in space as comfortable and safe as possible, space motion sickness is inevitable. Space motion sickness makes astronauts feel weak and suffer vertigo and nausea, sometimes for periods of 3 or 4 days. There are also psychological problems. The astronauts live in a closed space, cannot isolate themselves from each other, and are in constant communication with Earth. They sometimes become anxious, aggressive. What's the purpose of all this? Well, for their part, scientists are convinced that space is destined to become an exceptional research laboratory. With the advent of space shuttles and laboratories, space has become a much sought-after environment for scientific experimentation. Space's greatest asset in this regard is its phenomenon of weightlessness. In a state of weightlessness, it is possible to produce and study pure crystals. These crystals will soon be able to contribute to the development of electronics. Zero gravity also facilitates experiments designed to produce perfectly homogeneous metal alloys. On Earth, heavy atoms fall to the bottom of the compound, while the light ones have a tendency to float on the top. Where there is zero gravity, the atoms blend evenly. Electrophoresis, a technique consisting of separating the components of a biological substance by electric stimulation, is also much more effective in weightlessness. Not only can up to 700 times more particles be produced, but the substances obtained are far purer than anything produced on Earth. So space labs might yield a new generation of drugs that would be more effective because of being purer and more selective. The effects of zero gravity on the human body are also being much researched. Study has shown, for example, that the bone structure is disturbed in weightless states. The spinal discs, normally compressed on Earth by body weight, move away from each other in zero gravity. Astronauts have gained from 2 to 4 centimeters in length while in space. However, this lengthening of the spinal column disappears when they return to Earth, where, under the influence of gravity, the discs are forced back into place. The highly complex system of calcium fixation in bones is also thrown out of whack. In zero gravity, bones tend to be underused as they no longer have a load to carry. The bones adjust to these conditions, especially those of the lower limbs, and thereby lose some of their calcium. They decrease in density and weaken. These effects on the human skeleton vary from one subject to another, and according to the durations of flights. Worth noting is the fact that 10 years after having spent 3 months in the Skylab, the astronauts still showed a calcium deficiency in their bones. Thus, bone remodeling would seem to be a factor that would limit the length of space flights. As weightlessness is prolonged, there is muscular atrophy as well. Astronauts no longer have to exert any effort to move about or move objects. The first muscles affected are the leg and back muscles, whose function on Earth is to resist gravity. Even the heart muscle is affected. No longer having to combat gravity in order to pump blood through the system, the heart beats faster and reduces in size. A 1% reduction in heart size has been observed in astronauts on Skylab missions, and this presents a problem of some concern for future long-term flights. Blood tests made on astronauts have revealed major changes in the bacteria, bacilli, and fungi that normally inhabit the human body. Such is the case, among others, of the Candida, a microscopic fungus found in abnormally high numbers in the throats of astronauts. This microscopic flora and fauna do not come from space. They have accompanied man in search of a milieu conducive to their proliferation. The first inhabitants of space therefore risk being particularly exposed to epidemics. Except for the loss of calcium or the slight reduction of the heart muscle, most problems associated with being in a state of weightlessness for long periods are short-lived. Regular exercise during flights or use of the pressure chamber, which draws the blood down into the lower limbs, can offset the seriousness of the problems related to returning to Earth. In short, experiments carried out to date seem to indicate that human beings are capable of adapting satisfactorily to weightlessness and of readjusting to Earth's gravity afterwards. However, we know little about the consequences of space flights lasting 2, 3, 4 years. Some believe that after such long periods in zero gravity, the astronauts would be beyond redemption. That is, incapable of surviving a return to Earth. Others are of the view that after a certain number of years of weightlessness, man would become a little like a monkey, handling objects equally well with his hands and feet because he would no longer require his feet to walk. It has even been suggested that couples procreating in space could, after several generations, produce offspring structured along a radial symmetry line, somewhat like starfish. At present, private industry is conducting research on the materials and drugs manufactured in space. All top secret, of course. So for the time being, it's difficult to predict to what extent humanity at large will in fact benefit from space research.